Welcome back to the deep dive. You know the drill. We take your sources, we strip away the noise, and we jump straight into the insights. Today we are wrestling with maybe the biggest question a curious mind can ask. How does all this staggering, beautiful, intricate complexity in the living world, how does it arise if there isn't a blueprint or, a designer guiding the process?
That's a really profound puzzle. And I mean, just look at the scale of the information we're talking about. Think about an old school computer, right? It holds a finite, measurable amount of data. But then you look at the human brain. You measure that in millions of kiloneurons. It's a staggering number. But then you zoom in even further, and a single cell of DNA holds digital information that is, what, 1,000 times the entire capacity of that computer?
1,000 times the data. And it's organized perfectly. It's executing code, all compressed into a microscopic nucleus. I mean, that's not just complex, it's elegant. And for centuries, that kind of elegance really only suggested one thing.
Right. And this brings us straight back to William Paley, 1802, and his natural theology. Paley's argument was foundational and, well, brilliantly simple. The argument from design. If you were walking across a field and you stumbled upon a watch, you wouldn't just assume it randomly assembled itself, you'd assume a watchmaker. So when you look at something infinitely more complex, like the human eye, you have to assume a conscious, divine watchmaker.
And the sources are very clear on this. Paley was passionate. He identified the mystery correctly. But his answer was, and I love this phrase, gloriously and utterly wrong.
Oh, it was. Because while Paley was right about the appearance of design, he just completely missed the engine behind it. The real solution came decades later with Charles Darwin, who proposed this utterly different process. Instead of conscious designer with foresight, we get natural selection, which our source material calls the blind watchmaker. It's blind, it's unconscious, automatic. It has absolutely zero foresight or purpose. It just accumulates what works.
Okay, so that brings us right to the core concept. If we agree nature looks designed, why can't sheer random chance create it?
Well, it comes down to probability and, how we define complexity. Complex things, watches, airliners, even earwigs, they're heterogeneous. They have lots of specific parts that all have to interact in a very specific way. They have a quality that's specifiable in advance. If you just randomly throw scrap metal around, you always get a scrap heap.
But the one specific arrangement that lets a Boeing 747 fly or combination lock open on, say, 1207, that's a predetermined arrangement.
Exactly. Hitting that specific combination on your lock is, what, 1 in 4,096? Manageable. But when you scale that up to life, the improbability just becomes overwhelming if you try to do it in a single step. And this is the perfect moment for that classic thought experiment. The monkey and the typewriter.
The Shakespearean monkey. The idea that, given enough time, a monkey typing randomly will eventually produce Shakespeare.
Yes, but let's get specific. Our sources use a simple 28-character phrase. Methinks it is like a weasel. Now, you have to calculate the odds of a monkey hitting that exact sequence of letters and spaces in one single go, assuming 26 letters and a space. So that's 27 possibilities for each of the 28 characters.
Okay, that sounds like an astronomical number.
It is. The odds are 1 in 10 followed by 40 zeros. That figure is literally millions of millions of millions of times the age of the universe. It's just not going to happen. And that is the fatal flaw in arguing that random chance alone creates complexity.
I think this is where so many of the popular anti-evolution arguments get stuck, isn't it? They correctly calculate the impossibility of that single-step miracle, but they miss the magic word.
They do. They confuse single-step selection with cumulative selection. Cumulative selection is that non-random force that changes the whole equation. It goes from impossible odds to, well, a certainty over time. It's the key that Paley never grasped.
Okay, let's look at the computer simulation that shows this. So instead of starting fresh every time, which is single step, we introduce inheritance and selection.
Correct. You start with a random jumble of letters, and you let it breed.
Okay.
You duplicate it, but you allow for a tiny random error, a mutation in that duplication process. Then the computer just selects the resulting phrase that is closest to the target. Methinks it is like a weasel. And that best fit phrase becomes the parent for the next generation.
So you're locking in the small positive steps. You're not rolling the cosmic dice from scratch every single time.
Exactly. The key insight here is that while the mutation part is random, natural selection, the cumulative part, is the absolute opposite of random. The process isn't chance at all. It's a predictable, non-random move towards complexity.
And how fast does the simulation actually get to the target phrase using this method?
Well, it's rapid. I mean, we go from odds that need billions of times the age of the universe to hitting the phrase in one experiment in 43 generations and another 64. It turns what looks like a miracle into a logical inevitability, as long as you have a way to copy and select. That really is the heart of the blind watchmaker.
Okay, so with that distinction clear that evolution is this cumulative, non-random sculpture, we need to see the real-world proof. How does this play out in organisms that just seem too perfectly built, like those master hunters of the night?
Let's talk about bats, specifically the small temperate bats. Their echolocation system it's just a marvel. It's not just making clicks and listening. It is a high-tech radar system.
Yeah, we read about the horseshoe bats and their Doppler shift technique. That sounds like something straight out of an advanced physics textbook.
It is. The bat has to find a tiny flying moth, and it has to do it against all the background noise of its own movement. So the Doppler shift is that change in frequency caused by relative movement. As the bat gets closer to its target, it has to constantly adjust the pitch of its outgoing hoots. Why?
To keep the returning echo at a fixed, precise pitch, right?
Precisely. They're aiming for the one specific frequency where their ears are maximally sensitive. It's an incredible filtering technique. And what's so fascinating is that the bat doesn't understand Doppler theory. Its brain doesn't have an equation written on it.
So the animal is like the police radar gun itself. It's just performing the calculation perfectly, but the complexity is baked into its structure, all developed not by conscious design, but by the relentless pressure of cumulative selection. That's incredible.
It absolutely is. And, if evolution were perfect, we'd only see these elegant solutions. But because evolution is constrained by history, it can only work with what's already there. We also see flaws. And sometimes those beautiful flaws are the most powerful proof we have.
Okay, give us the prime example of a beautifully flawed design.
The flatfish. The place, the soul, the flounder. If you were a designer starting from scratch, you'd give it symmetrical eyes on either side of its head. But its ancestors were normal, upright fish like a herring. When they moved down to the sea bottom, they started lying permanently on one side.
And one eye was just facing the sand.
Useless.
Totally useless. So instead of just growing a new eye on the top side, the existing lower eye had to migrate. Over many generations, the lower eye began to physically move over the top of the skull during development to join the other eye.
Wait, the eye actually moves across the skull.
Yes. If you look at an adult flatfish, its skull is permanently twisted, asymmetrical. It's this bizarre sort of Picasso-esque structure that no sensible engineer would ever choose. But because evolution had to solve the problem step by step from what it had, it ended up with this messy compromise. And that imperfection is just incredibly strong evidence of a gradual, constrained path.
That really brings it to life. It's not about being perfect, it's just about being good enough to survive. And this pressure repeats itself everywhere. That constraint, that cumulative pressure, it leads to what we call convergent evolution. That's where unrelated species in totally isolated parts of the world evolve similar forms because they're doing the same job, so to speak.
Right, like horses and those long extinct Litopterns in South America.
Exactly. The Litopterns were completely unrelated to our modern horse lineage, but they independently evolved legs that are, and this is a quote, all but indistinguishable from a horse's, right down to losing all but the middle toe. Why? Because if you live on open grassland, that specific adaptation for speed is what works.
But the behavioral convergence is almost more fascinating, especially with the social insects.
Oh, absolutely. The sources give this spectacular example of the New World army ants and the Old World driver ants. Two separate lineages, separated by an ocean, and they both independently evolved the complex legionary habit.
The terrifying wandering armies.
They don't build nests. They are massive nomadic supercolonies. They march across the landscape carrying the queen and all the brood with them. This huge, coordinated, intricate social behavior was invented not once, but twice, because that lifestyle, large-scale mobile pillaging, was just the most successful strategy in those environments.
Okay, so all of this evidence relies on this principle of gradual, step-by-step change. But this is where the skeptical challenge always comes in. What good is half a lung? What good is half a wing? I mean, if a feature only works when it's 100% complete, then the whole theory fails.
And that challenge is built on, well, a basic misunderstanding of biology. These complex features are almost never all or nothing. They're almost always continuous variables. Take lung area. The human lung has a massive surface area, maybe 70 square yards, built with this recursive branching structure.
And if you reduce that area, you don't just drop dead. Of course not. People live productive lives with just one lung, maybe a third of the normal area. The effect of a smaller lung is gradual. It just affects how far you can walk or how fast. There's a perfect continuity all the way down. A fish flopping onto land for a few moments benefits from even 1/100th of a lung. It lets it survive just a little bit longer.
So if you apply that same thinking to the half-a-wing problem, the utility is immediate. I mean, we see modern gliding animals, flying squirrels, some snakes that have these little proto-wings or flaps of skin.
And any slight increase in that surface area helps. If you're falling from a tree, even the slightest ability to brug your fall or control your leap can be the difference between life and death. It's simple, really. A fraction of x is always better than no x at all, if x provides any advantage.
So once you have that gradual utility, what is it that drives the complexity forward so quickly? That would be the evolutionary arms races. These races, like between a cheetah and a gazelle, are the primary engine of what looks like progress in evolution. The gazelle gets faster, which selects for a slightly faster cheetah, which selects for an even faster gazelle, and on and on.
It's an upward spiral of sophistication, and we actually see hard evidence for this in the fossil record.
We do. Studies of fossil skulls show a clear trend. Later carnivores consistently had larger brains than earlier carnivores, and later herbivores had larger brains than earlier herbivores. It shows this sustained, bilateral brain-size arms race over geological time. Both sides are being pushed to get smarter, more complex.
But these races can't go on forever, right? They have to stabilize at some point.
They do. They stabilize because of economic pressures. Evolution is ruthless about resource allocation. High speed needs heavy muscles, which are expensive to build and maintain. That's energy that could be spent on, say, producing more milk for your cubs. There's an optimum point of investment, and once that's reached, the race slows down.
Okay, let's bring it all back to the core information technology here. The DNA. You called it the digital archive.
It's the ultimate ROM, read-only memory. The instructions are burned in at conception and copied. The genetic changes, the mutations, provide the random variation, and then the non-random survival of the individuals with successful mutations effectively writes better instructions into the species' genetic memory over generations.
That's a huge chain of causality. The sources had a great anecdote about a beaver mutation that makes it all click.
It's perfect. It connects a tiny genetic change to this massive ecological structure. So a minute change in DNA causes a subtle difference in the beaver's brain. This might just make the beaver hold his head a fraction higher while it's swimming with a log. A tiny change, but it has a huge effect. It slightly reduces the mud washing off the log, making the log stickier for building the dam.
So the dam is better, more
Yeah.
secure.
Which means the offspring survive at a higher rate, and those successful offspring inherit that exact gene for the head-lifting behavior. That's cumulative selection right there. A blind, automatic force selecting for better dams based on a tiny change in posture.
So to wrap up the main mission for you, our listener, today, the apparent miracle of design is resolved. It's resolved by the non-random power of cumulative selection, acting on random variation over vast stretches of time. It builds complexity through small, self-reinforcing steps.
That is the Darwinian resolution to Paley's great challenge. But that resolution immediately forces us to confront the one huge remaining question, one that is still staggering.
The ultimate origin. Where did the whole system even begin?
Exactly. We've shown that cumulative selection is incredibly powerful once it gets started. But before it can start, you need a basic replicator, the first molecule that can make a copy of itself. The origin of that first replicator had to be a single step chance event. The probability of this spontaneous generation, or SGP, is vanishingly small. It is, by our standards, a miracle.
So we're back to those astronomical odds. But this time, there was no cumulative selection to help. It just had to happen once.
Exactly. And the crucial point from the sources is that while the SGP is tiny, maybe 1 in 10 to the 40, or even lower, the universe gives us enormous statistical room to play with. We know life arose here on Earth.
And the sheer size of the cosmos changes what we can consider probable.
If you accept the estimates that the universe might have, say, 100 billion suitable planets,
Ooh.
then the maximum amount of luck we're allowed to assume in our theory is inversely proportional to that number. We can afford an event with odds of 1 in 100 billion and still be unique. But if the required luck was less than that, life must be common.
That's the stunning final thought, isn't it? The complexity we see here is resolved, but it forces us to apply a cosmic scale to our own existence. We are here, built by the Blind Watchmaker, but our very presence required that staggering one-time chance event to kick it all off.
And the fact that the process began pushes us to ask, what is the true SGP? Did it take almost all the luck the universe could possibly offer us? Or was the formation of that first replicator actually much, much more probable than we think?
What is the true spontaneous generation probability? How rare or how common are we? That's the ultimate deep dive, and that is where we leave you to mull today.